Okay, hello to the next installment. Let's dive right in. So, recap of where we are. We have a test program that creates a path that goes through the various 6502 features, and hopefully this path takes us to all features of the 6502, so that if we follow that path, we have no choice but to create compatible implementation. We ran that path through an authoritative emulator that tells us, that can make sure that the path draws the correct framework within which, the correct groove in the ground, if you will, in which we have to maintain ourselves. And we started walking that groove. And right now, we got to 200 cycles. 200 cycles where the whole program is here. We want this entry. The whole program is 9,500 cycles. So we're about 2% in. Cool. I'm a bit sick. I hope I survive this. Okay, so what we have is new feature. I do this, and I no longer hide half the screen. So, we are at opcode A0, which is unsupported at cycle 201, and if we load the test program, we see that cycle 201 is load Y, immediate. So let's try something and see if it works. We can go to opcodes and search for load Y and see that A0 is indeed immediate. But if we just go to the CPU implementation, which is here, and we can just implement it. We can go to the Visual 6502 and explicitly check cycle by cycle how this works. But we already know how this works because we already have load A immediate and load X immediate. So there's no need for that. Instead, we can just go into case 0xA0, spell 0 correctly, op load Y, LDR mode immediate. Now, of course, we will need the .h and op ld. We don't have LDY, so we will need to add it. And then, if we go here, actually this implementation is incomplete. So let's let's do a complete implementation. A complete implementation of the thing we're missing is the condition codes. So if you look at the code we actually have, we just fill in the register from memory, and we can do that very easily. We can just do rig Y and we're done. But that doesn't really do everything the opcode is supposed to do. You'll notice that the opcode is supposed to also update the negative and 0 flags. So let's add those now. So now we look at reg Y, and what we need to do is, let's just copy the condition codes reg status. No, sorry, I forgot how those work. we get CC and CC set, right? So we want to say CC set of a CC 0, and the value is reg y equals 0. So that sets the 0 flag. We're worried. Load y. And the negative flag is just CC set, CC negative for reg y and 0x80. So we check whether the high bit, the seventh bit of the register is set, and if so, the negative flag needs to be set. And we can copy those here and here, of course, changing y to a and y to x. So this should do it. And if everything goes well, we should get past, right, we advanced 2 more cycles to command 8a. Command, that's cycle 203, and command 8a is transfer x to a. So again, we go here, transfer x to a, and we see that it too affects the condition code. So it says copy x to a, and okay, so 8a I think we should get out of caps lock. Okay, case 8a, op transfer xa, ADDR mode. I think the other transfers implicit, right? Implicit, and we need to op transfer xa, edit declaration, and let's open another window. Aha. And again, we see that we haven't updated the flags. So I think further down in the program, in the test program, there is a code that is actually meant to check whether we updated the flags. We can verify that, but I won't rely on it, and I'll update the flags now. So essentially, it's the same code as we did for the op LDY. So we go transfer XS. Wait, transfer XS doesn't update the flags, so we don't want it here. But actually, we do want it here because that's transfer XA, and that's reg A, and that's reg A, and that's reg A. Okay. So what you'll notice, okay, 208. 208, that's transfer Y, A. So we want transfer YA, and we want transfer YA. Let me explain what we're going to see in a minute. Very soon, we're going to start hitting opcodes that we've already did, and only with different addressing modes. So what happens is that right now we spend about 50 seconds to a minute on each opcode. And as we continue, the amount of time we spend on each opcode goes down, as a rule, but there will be exceptions. as each opcode becomes more effective, it has more effects. So we'll begin to see that very shortly, and I'm hoping that in about 15 minutes, 20 minutes, we'll get to the interesting effects, which are the interrupts and the reset sequence. So hold on, and if you're watching the recording, feel free to skip forward. Okay. Where were we? We were at 9.8, and we said that 9.8 is transfer YA. And so we go to the switch. Case 9A of transfer YA of ADR mode implicit. So a lot of boilerplate at this point, and like I said, it should get slightly better in a moment. We already have 9A. It says that that's because that's 9.8. Okay. 215. You'll notice that we jumped quite a few cycles with one work because these were already implemented. Store A 1F5E. I think that's the first time we have a store operation. So let's linger on that one. So if we go to the browser, and at this point I'd like to point out that I really ask you to check out my Patreon page. If you enjoy these videos, supporting me on Patreon would be really helpful to me. But going back here, we are on opcode 8D, and that's store A to absolute value. So 8D to let's use the code here, FE01. FE01. And let's see how the execution works. So we reset the CPU, and here it goes. First cycle, we read the opcode as before. Second cycle, we read the lowest significant byte of the address. Third cycle, we read the most significant byte of the address. And then fourth byte, we just perform a write, 0 here means a write, to the address we wrote. And that's it, we're on to the next instruction. So nothing very groundbreaking. One last thing we need to check is if we go to store A, it doesn't affect the condition codes. So that's that. Okay, so 8D, case 8D, op store A, ADR mode absolute. And then, do we have that defined? Oh, we already have that defined. So that's it. That's the beauty of the condensation. So we have the addressing mode already defined, and we have the opcode already defined. So essentially, we don't need to do anything. We don't have to define the actual function. We just add the line to the case, and we're done. In fact, let's add a couple more lines from the same command. So we have 8D, and we already have 8.5. So we have 8D and we have 8.5. Let's see what 9D is. Okay, those are addressing mode we don't have yet. No, let's wait until we actually run across them, and then we'll implement them. So compile, and we should get much further. Oh, much further. We were at 215, and we're down to 311 cycles just by adding this one line to the code. 311 is, this command is called set carry. It's very complicated command. It goes 1 into the carry, and we see that the condition codes affected are the carry gets 1. Very complicated. So, do we have any of those? Why do I get uppercase all the time? No, we do not. Okay, so op SEC, and we'll ask for address despite the fact that we don't actually need them. And okay, let's do the implementation. So the opcode is 38 op SEC ADDR mode implicit. Let's go to the actual implementation. So void C6502 op SEC ADDR, and what we do is cc set cc carry true. Pretty straightforward, if you come to think of it. Let's see if that worked. We need the correct amount of columns. And that gave us 40 more cycles. 352 F8. I'm going to guess, because of the 8, that this is also set or clear. Let's see. 352 set decimal. I was right. Let me show you. This is an interesting decision by the creators of the 6502. You see under the column 8, the column 8 is the lower 4 bits of the opcode. We have clear carry, and then 2 below we have set carry, and then 2 below we have clear interrupt mask, interrupt disable, and then 2 below we have set interrupt disable, and then 2 below we actually have unrelated opcode, and then we have clear overflow, and then clear decimal and set decimal. So aside from clear overflow, the same bit pattern matches all clear instructions and all set instructions. And this greatly simplifies the 6502 address decoding. That's what allowed me to look at 8 as something F8 and say, oh, that's something, set something. In which case we said set decimal. So we have set carry, set decimal, and set interrupt mask, and those set the decimal and interrupt mask. And we also have the clear carry, it's actually CLC, which is the same thing except false, and the clear decimal, which again is false, and the clear interrupt mask. And we also have the clear overflow. This is, I think it will become more understood when we get to the external signals. But there's a clear overflow, but not a set overflow because of reasons. We'll get to them when we get to the signals. I hope it will be today. Okay, we need to add declarations to all of those. So set carry, set decimal, and set interrupt. and also clear carry decimal and interrupt, and also clear overflow. And now we need to add the opcodes. So set decimal and set interrupt, which are at set decimal is F and set interrupt is 7. And then we want the clears which are 2 below. So that's 1, that's D, and that's 5. Let's see if I haven't made a stupid mistake. D is clear decimal, and 5 is clear interrupt, and clear carry, clear overflow is B. Let's see if that even compiles. Of course it's not, doesn't. LDR has not been declared in H. Right. And we're up to 610. Just remember that we started this video, we were at 200. We were at cycle 200. We're 20 minutes in and we're already at cycle 600. Okay, command BD at 610. So that's load A absolute plus X. Okay. So that's a new addressing mode. So let's begin by just writing it in, even though it's not defined. So case 0x BD op load A ADDR mode absolute plus X. And that of course won't compile because we haven't declared this mode. So let's declare it absolute plus X. And we need to define it. So far, so good. So that's absolute. What does absolute plus X do? So if I just leave it like that, it fails because we read it from the wrong address. So how does ADDR plus X work? We were at BD, right? So BD, and let's see how that works. So first cycle, we read the opcode as usual. Second cycle, we read the least significant byte of the absolute address, and then the most significant byte of the last absolute address. So that gives us 01FE. You know what I want to build? I won't start with this. I want to start with something a bit lower. So 03. Okay, let's try it. So 0301. So the address is 103, and then we read from 103, which makes no sense because that's not where we want to read. Okay, no, it is. Sorry. Okay, let's set X to let's set X load X immediate is a 2. So let's set load X immediate with a value of 3, that's fine. And then BD, why does it keep jumping like that? BD, which is load A absolute plus X, to whatever, a 41, 41, 01. Okay, so let's see how that works. So we load the x immediate and we read the value 3. And then you'll notice, okay, x already got the value 3. Load a absolute plus x. We read the least significant byte and then the most significant byte. So that's 0141. And then we need to read from 0144. And that happens on the next cycle. However, if I replace 41 with FE, look what happens. So we read from we read the opcode, we read the least significant byte of the address, we read the most significant byte of the address, and then we read from something which is completely the wrong address. It's 0101. But then we read from the correct address, 0201. So what you'll notice is that, first of all, the command took one cycle longer. And the second thing you'll notice is that it read from the wrong address in this extra cycle. What happens here is that the ordering of memory, of the data in memory is frankly quite genius. It works like this. It reads the least significant byte of the destination. And now it needs to do an ALU operation. It needs to add x to that. And it needs a whole cycle in order to do that. So it does that using this cycle. So the cycle it reads from the most significant byte from memory is the same cycle it adds x to the least significant byte. And if that doesn't overflow, then in the next cycle, we can already read from the correct address, load A into memory, and we're done. However, if it does overflow, we need to update the most significant byte, and that needs another ALU operation, so another cycle. So this is what happens at this cycle. So we need to encode that into our absolute plus x addressing mode. So it goes like this. We read the program counter, that's the result. Fine. And then we advance PC. And now we read the program counter again, and that's the high part of the result, which is also fine. But then we need to do this. We need to, so what we'll do, res high and res low. So we'll read the program counter into res low and advance the PC. And then we'll do, we read the next byte into res high, and we'll do res low plus reg x and advance the PC. Now, if res low and so the high byte of, res low shifted right by 8 bits is 0 or is not 0, then we need another cycle. So we perform a read from a composition of a res high shifted right by 8 bits and res low and 0xFF. So that's a read from the wrong location. And that's it. And then we go return res low plus res high. Res low, remember, will have the 1 bit in the most significant byte if it overflowed. So that will always return the right value. And if we need to, we take, this means we take an extra cycle. So that should emulate precisely the original 6502. Let's see how closely we got it. Close enough to move another 100 cycles forward. Cool. No, that's not 100 cycles. That's just a few. Okay. Load A absolute test plus y. So plus y is exactly the same as plus x, except it uses y, which is kind of understandable. And that's a B9. B9 absolute y. $631. Load A 0-page test plus x. Now, 0-page plus x works differently from absolute plus x because essentially it doesn't care about overflows. So the fact that it overflows doesn't matter for the number of cycles. We can just go ahead 0-page plus x goes return ADDR plus reg x truncated to the lower 8 bits. So it's always in the first page. And we need case, what code was it? B5. That's op LDA ADDR mode 0-page plus x. Redefinition of LDR mode 0-page. Yeah, when is right is right. Okay, 633. We read from the wrong location. We expected E9 and got A9. Okay, so obviously we got something wrong. Let's verify that that I correctly characterized 0-page plus x. That's B5. B5 FE. That's fine. Okay. Load x with 3. Load A 0-page. We read the location in 0-page. And then, okay, sorry, my bad. Remember how I said that we need the cycle in which we read the most significant byte of the address in order to calculate the ALU? Well, here we don't have a most significant address, so we don't have time to do that. We have to explicitly waste a cycle on that. So we need to account for that in here. So we advance the program counter, that's fine. And then we read from ADDR. And then we return the addition. And we got further. No, we didn't. Yeah, we did. On command B1. Load A. Okay, this is an interesting code. We read a 0-page address, and then we read 2 bytes from this address, from the address and the address plus 1. Then we add y to that address, and we read from that address. So, let's see. That's load x. Let's load y with the value. Load y is A0. So let's go A0, A24, and then the command we want to test is B1. B1. And now we have two overflows we can handle, right? The first overflow is what happens if you wrap around in 0 page, and that happens if you read from FF. And generally speaking, the answer is nothing. We don't care about that overflow. But then we do care about where that address points. So if we read from FF, the address will be reading the least significant byte of the address will be here at 0FF. Let's put that 45. And the most significant byte will be here. So let's see how that works. So we set X, we set Y, that's fine. And then we go load A from 0 page plus Y. And then we read from FF, which is the, we read the program counter, which tells us the address in 0 page is FF. And then we read from FF, and we read from 00, so that's the wraparound in 0 page. And we compose the address A245. We add 24 to that to get 4 plus 5 is 9, so A269. And then we should be able to read from A269. Yeah, that works as you'd expect. It gets more interesting if there's a wraparound on the calculation. So if we, instead of 45, here I put F5, and we try this again, we load X, we load Y, and then we read the address, we read from the address F5, we read from the next address A2, so far so good, and then we read from A219, which is not the correct address, because we should have wrapped around the most significant byte, but again, we didn't have the cycles to do that, so it's only on the next cycle we actually read from the correct address. And again, if there's a wraparound, this command takes one extra cycle. So we need to account for that. Okay. He goes. I'll call the addressing mode 0 page indirect plus Y, and we'll set that was B1. So case B1 op LDA from ADDR mode 0 page indirect Y. And we'll copy 0 page indirect Y. Oh, so recap. We read from the program counter, that gives us the 0 page address where everything is hooked on. So that's the address. And now we read the least significant least significant byte. We read from ADDR. So that's one cycle. And then we do two things. The first thing is we add to res LSB reg Y. And the second is we read for res MSB ADDR plus 1 truncated to 8 bits because we need to stay on the 0 page. And now, and we shift that by 8 bits. And now the main question we need to ask ourselves is, did we overflow? So if res LSB 8 is not 0, so we overflowed. We need to perform another sort of dummy read. And the read is from the composition of res most significant, let's not shift it. Res most significant bit and res least significant bit lower 8 bits. So that's the dummy operation. And then we return res LSB plus res MSB shifted right. Let's multiply it by 256. It's the same thing. And let's balance our parentheses. And we moved on by 30 cycles. Cool. Unknown command E. Sorry, by more than, we moved on by, yeah, but quite a few cycles. We are at 10% of the whole test lab. Arithmetic shift left or absolute. Cool. So let me just sort this so it will be in the correct order. Okay. We're at 0E of ASL of ADDR mode. Let's see. 0E absolute. The A here means we're at absolute addressing. Absolute. Let's implement the op ASL ADDR. Okay. ASL. Let's see what the actual command is. The actual command is we shift everything left into the carry. So we put a 0 in from this end, and the bit 7 goes into the carry. And beside the carry, we also need to update the negative and 0 flags. Okay. That's going to be a bit of a challenge. Okay, so first of all, we want to read from ADDR. And okay, and that's a read modify write command. So it means that we don't affect, you'll notice that we don't affect any of the registers, besides the status flags, we don't affect any of the registers. We read value from memory, we manipulate it, we write back to memory. Okay, so uint ht value, except because I need an overflow, I'm not putting it in an 8-bit value, I'm putting it in a 16-bit value. So now, shift the value left by 1 bit. And when you do that, you need to waste a cycle, because this takes a cycle to do on the 6502. So the question is, what does it do during that cycle? And the answer is nonsense, absolute nonsense. This is opcode 0E. I'll show you just how much nonsense it does. Okay, so 0E, and that's an absolute address. So let's rotate this location. We'll put here F4. So we'll go 6C00. So that's the address we're rotating. Okay, reset the CPU. Here goes. Arithmetic shift left. Read the least significant byte of the address. Read the most significant byte of the address. Read the actual address. So up to here, we're just reading the data in. And now we need a cycle in order to process this information, this data. And during that cycle, we write, see this 0 here? We write the old value back into the same address, which is absolutely bonkers. And then we write the new value into the same address. What you'll also notice is that the negative flag is set, the 0 flag was clear, and the carry flag was set. So we kind of knew that was going to happen. Okay, bonkers though it is, that's what we're going to do. So before we rotate the value, we write ADDR, write value back to the memory, and then we write ADDR val again. Like I said, bonkers. What we also need to do is, at this point, CC set. Okay, here goes. We want the carry to be set based on the question of val and so whether we overflowed a 1 into the whether the number was negative before we shifted it. The negative is set based on val and whether it's currently negative, and the 0 is set based on whether val equals 0. That should work. 695. Yep. And at this point, these are just technical. We go, oh, 1e is the same but at absolute plus x. And validation failed on the plan, write operation where read was expected. Okay, that's strange. Okay, we've got a bug. Let's try and figure out what it is. We're doing arithmetic shift left of the value plus x. So we're reading the least significant byte, which is 1, 0, and the most significant byte, which is 8, 5. And then we're reading from A5D0, which is 4, 0. And then we're reading from A5D0 again. Okay, I think, and then we do the two. So we're doing a dummy read, despite the fact that that we didn't actually we didn't overflow the most significant byte. I think I saw something in the errata. Let's see here. For ASL instructions, bit 7, okay, no, that's not interesting. Memory lock, which is kind of useless. No, the datasheet doesn't say anything about it. That is the absolute beauty of what we're doing here. We've got something that behaves differently from what the datasheet says it's going to. So the datasheet clearly says how this is going to behave, and the CPU behaves differently, takes an extra cycle. And we would never have caught it if we went by the datasheet. The only way to catch it is to do what we're doing, to compare against actual execution. So, the problem is that now we do not understand why, but we need to accept it as is. So what we'll do, we'll go if essentially this is a problem because the code to duplicate, I think this won't happen if we actually do need. Okay, so what we'll do is we'll give absolute x a value true here, and ADR mode absolute x, and it will go bool a always waste cycle equals false. And then go if this or always waste cycle. Okay, that should do it. And this way we're saying if this is an arithmetic shift left, always waste that cycle, even if it does, the value doesn't overflow. Yeah, and we passed that point. Whew. Okay. 0 page. That's 06. Op ASL ADDR mode. 0 page. What you'll notice is that I'm no longer actually writing code. I'm just hooking opcodes I've already written with addressing modes I've already written. So again, 1, and that's 0 page dash x. And what you'll notice is that we just added 100 cycles of runtime just like that. And then we get to this instruction. And the thing about this instruction is that it's not the same instruction. It looks like the same instruction. It looks like we'll just need to pass something to ASL, op ASL, but it actually isn't, because 0A means that we're not shifting something in memory, we are shifting the accumulator. And if we actually look at the execution, 0A, one cycle to read the opcode, one cycle to read the next instruction, even though it's irrelevant, and that's it, we're done. And A is shifted. Admittedly, it is only shifted in the cycle after we expect it to, but that has to do with the way that the 6502 is built, which is very pipelined. So, what we need to do here is give it a completely different implementation of arithmetic shift left if the destination is the accumulator. And actually we can skip the address. This one will never accept address. So that was 0A. Of ASLA. And what we need to do is we need to read the program counter, because we need to waste a cycle, but not advance the program counter. And then we go pretty much the same as here. So val is reg A, val shifted left by 1, and then the condition codes and reg A equals val. So it's not a very different implementation, but it's different enough that we can't merge them into a single instruction, into a single function. But if you look at the bit assignment, you'll notice that it's sort of a bastard son anyway. So those go on E and 6, and all of a sudden this goes on A, which isn't the same. So 0A has all of the accumulator-based instructions. So I feel fine with that. We were at 828. We got to 934. 934. Okay, that was unexpected. 934. We were at the push flags. What did we do wrong? Write of wrong value to memory, expected 3.3, got 3.1. Which means that one of the, another good catch by the test program. It means that one of the instructions we ran didn't set the flags correctly. So PHP, what it does is it pushes the condition codes into the stack. And it expected us to write 3.3 at this point, but instead we wrote 3.1. So if we look at the opcode, the 0 flag was supposed to be set, but was not set. Okay. So now we need to go back in the program and see what was the last thing we ran before it. And we see the jump subroutine to flags dump. That's the code in the test program that makes sure that the flags were set correctly, which now you know why it was there. And the first instruction before that, so that's at 370. If we load the test program, yeah, no, that's not as useful as I thought. Okay, forget it. That's the arithmetic shift left of absolute plus x. So we did something wrong. We were supposed to be at 0 at this point, but we were not. Okay, so let's look at the test program. And let's look for ASL absolute test plus x. So that's the line that didn't run correctly. What we can do in order to figure out what the problem is add here store A to some dummy location. And in fact, I have a dummy location, value dump. So store A to value dump. And this will trigger the problem earlier. So now we need to go back to the test harness, go to the test program and compile it. Sorry. test program, compile it with the CPU set to MOS, and then go to the Perfect 6502 and run the simulation. And what happens now is that the test plan changed. It incorporated the new instruction we just added. I can't stop being excited about this. What happened here is that we wrote in a fairly high level of abstraction that we want a different test to run, and we just ran two commands, took a few seconds, and we have a new test plan ready to verify our CPU. I think it's amazing. I know nobody else thinks so, but I don't care. And now we go make again, and the verification failed on line 942. No, still on the push flags, which means the value is correct. So if I scroll up, the store A value dump, the value we write is correct. We write 0. But for some reason, we didn't set the 0 flag. So let's look at our ASL implementation. Right. Yeah. So what we need to do is go val and equals ff. We need to truncate value. Otherwise, this test won't run correctly, and we need to do it here as well. And now it should work. And again, my mind is blown that what chance would we have of catching this bug if we didn't have this? It was so easy to miss this bug. But we spent, what, 5 minutes on it? Instead of putting it into production, letting it run, and then on some rare occasion have it run incorrectly and then try to pull out hairs. See the bold spot? Pull out hair, figuring why it didn't run. Not only that, but you'll notice that we're 2,500 cycles into the test plan. So we're way into the test plan. We're working. Yeah, I know nobody else is excited about this. I know. And we're at the next instruction. So I think, first of all, I noticed that I lost all of my live viewers. I think that's a good point to stop. The next session will not be the same type of session. I'm going to resolve all of the just plain boring instructions, and I'll probably leave the handling of the asynchronous signals till next session. So it will probably, I'm hoping it will be a shorter session as well. So thank you everyone that made it this far into the video. I'm amazed. Way to go. Thank you very much. See you next time.